Okay, so welcome back to our course on the fundamentals of attosecond science and technology, brought to you from IIT Madras and IIT Tirupati. This course FAST is now in its week 4, and we are currently in the module on femtosecond laser pulses, and this is the 5th lecture of this module. Once again, we refer to these classic texts, the one by Roulier, femtosecond laser pulses, the principles of optics, Born and Wolf, and the relatively new text, Fundamentals of Attosecond Optics by Professor Chang. And as always, I am grateful to Professor Trebino for sharing materials and inputs. In today's lecture, we will do a bit of recap from the last week and probably little more. Firstly, we had discussed about the formal description of pulses in the temporal domain. We introduced the formal description. We also had a recap of the Fourier transform toolbox, which essentially helped us to recall some of the essential tools from this very important mathematical enabler, and which we will not go into once again. I just wanted to bring this up to your attention that we did this, and we need to keep this handy always. And we will also look at the frequency domain description in brief as a recap. But in today's lecture, we will peer into the details of femtosecond pulses as we should know, and in some sense things start to get real. So, in today's lecture, we will endeavor to cover these concepts or nuances, which are very important in our formal description of optical pulses and also perhaps beyond. So, these would be the concepts of instantaneous frequency and the phase terms that go into the formal description of pulses and the interpretation, and for the first time in this course talk about the chirp of a pulse and the characteristics of chirp pulses. So, this will be the main burden of discussion today. So, now for a relatively quick recap about optical light pulses and their formal description in the time and frequency domains. Recall that in the time domain, the electric field of the pulse, which is real, is written in terms of the envelope function, which is the square root of I of t, I being the intensity, and exponent of I omega naught t minus phi of t, phi being the phase term, where omega naught is the carrier frequency and it captures the fast oscillations under the envelope. The phi of t term is everything else in the phase. So, evidently this variation in time, both of phi of t and I of t, are slower than that of omega naught t. Okay. So, now if we throw away the fast carrier oscillations and build the so called complex amplitude of the pulse, which we call E of t, it is proportional to the square root of I of t, where I is the intensity function. So, the time variation of the intensity function pertains only to the envelope, and exponent of I phi t, where phi of t is the phase term. Square root of I of t is often called the real amplitude, which sometimes in literature is given the nomenclature A of t, whereas E of t is essentially the complex amplitude, which is the real amplitude multiplied by the exponent of I phi. And for a quick look, the carrier oscillations, which are the dotted lines corresponding to the fast oscillations of the electric field, and the envelope of the electric field, this is the gray curve, which for us is the square root of I of t, and the red curve, which is simply I of t. The intensity envelope are all sketched here for a Gaussian pulse, whose intensity envelope has a width that is a square root of 2 shorter than the width of the real amplitude. Now, the same pulse can be described equally well in the frequency domain entirely and in as complete a way as the time domain, which is the first equation here. E of t is a half square root of I of t exponent of I omega naught t minus phi of t. Note the fact that here it is an equality. We have set the system of units such that we can write this expression as it is, and of course, we always had the plus complex conjugate, so that the left hand side remains real. So, equivalently we can in this case now write the same expression down in the frequency domain, where we have E tilde of omega is a half, and we have a term mimicking the real amplitude in the time domain, here being replaced with something similar, which is the square root of the spectrum, the function that describes the spectrum S of omega. And now instead of the temporal phase phi of t, we have the spectral phase, which is another phi of omega, both are phi's, remember, and some kind of lowercase phi. So, we should really be aware from the context as to which domain the phi belongs to. So, it is important always to write down whether it is in the time or the frequency domain, and from carrying out a similar exercise on the complex conjugate part, we get the second term, which essentially contains frequency terms, or in these cases where all the frequencies together are negative. Omega and omega naught are positive numbers because frequencies are positive definite, whereas here it is minus a omega and minus a omega naught, whereas here for phi it is also minus omega and minus omega naught. So, we do have this negative frequency aspect coming in, because we have two terms in the definition of the temporal definition of the field. However, the negative frequency component contains no new information. So, therefore, in the spirit of defining the complex envelope in the time domain, we now take the same approach in the frequency domain. So that we have E tilde of omega is the square root of an intensity like quantity here, but in the spectral domain, which is the spectrum S, a function of omega, and we have the spectral phase exponent of I phi of omega coming in. So, this is these two domains are equivalent, and we have equivalent descriptions of the two in both these cases, right. So, now put everything together in the temporal in the frequency domain rather. In the temporal domain, we had the full description of the field, which is E, the script E of t, which contains not only the complex amplitude, but also the fast carrier oscillations. E of t, the complex amplitude, which is the real amplitude times e to the minus I phi of t, where phi of t is this temporal phase function. Now, with these two functions yield us with essentially 3 spectral domain functions, of which E tilde of omega, which is the Fourier transform of the complex envelope E of t, is a function which is centered at with a frequency of 0, because we have knocked off the carrier frequency from this function. Okay. So, this is essentially a function which is a shifted version of the E tilde function's positive frequency side moved behind by omega naught. So, this entity to the right pertaining to script E tilde of omega pertains to the Fourier transforming one aspect of the two complex conjugate pieces that formed E of omega in the time domain. This is one piece of it, Fourier transform. This gives us the positive frequency side in terms of the amplitude of the spectral domain description. So, this envelope which we see here in gray is the square root now of S of omega, okay. And this is the dotted line here is the spectral phase function phi of omega. Its partner on the negative frequency side is once again this gray envelope, and we have the dotted spectral phase once again. Okay. So, as is evident, since these functions, the square root of S or phi of omega are essentially what we care about is the mathematical form or the shape of these functions, which contains all the information we need, apart from the carrier frequency being just a number, right. These two pieces are identical, okay. albeit the spectral domain function essentially is very similar. We can transform one of these pieces to the other in terms of the spectral phase also. That is to say, no new information is contained on the negative frequency side, which is a bit of a relief, because we cannot measure negative frequencies, and therefore, the fact that we do not need to, and the fact that this is merely a consequence of our adopting certain mathematical notations is very reassuring. Okay. So, now just as we had in the time domain, where we had intensity, amplitude and phase, in the spectral domain we have spectrum and spectral phase both, right. So, spectrum and spectral phase are obtained therefore from the frequency domain description of the field in much the same way as intensity and phase from the time domain. So, if I know E tilde of omega entirely, okay, this is the electric field in the spectral domain. Tilde denotes the Fourier transform. Once again, let us recall that that is the Fourier transform from the time to frequency domain. Then the spectrum is by definition the absolute value square of this function. The fact that this is the absolute value square means that the phase factors exponent of I phi of omega and anything else in the phase factor gets essentially knocked off, and we are left with just the remaining part. So, the spectrum contains no phase information, and the phase function, the spectral phase function phi of omega itself is minus the inverse tan or arctan of the imaginary part of E tilde divided by the real part of E tilde, or equivalently it is minus 1 multiplying the imaginary part of the logarithm of E tilde. Okay. We also now looked at a Gaussian pulse, which is a simple idealized pulse where the Gaussian is real and its phase is essentially 0. That is, phi of t was in this case is identically 0 across all time. That is the description of the pulse. This is the pulse we have chosen. So, here we essentially learned how to essentially get a portrait of the of a laser pulse. We are habituated to sketching only either the time of frequency domain envelope, which is here the red curve or the bottom or the green curve in the bottom plot, but then a complete description of the pulse in either domain should essentially involve plotting also the temporal phase, or for that matter the spectral phase, as the case may be. So, therefore, a proper description of an optical pulse in the femtosecond or any domain for that matter should in graphically should contain the time axis or the frequency axis and an intensity axis, the temporal intensity axis or the spectral intensity axis, and we need a second vertical axis, okay, which is the phase axis, the temporal phase or the spectral phase, as the case may be. Okay. So, this is the most compact way of getting the details of the pulse into one postcard. So, let us keep this in mind. So, if the temporal phase function is a constant and a 0, so is the spectral phase function. Now, we also saw an interpretation of what the spectral phase means. So, we took the very simple case, instructive case of setting phi of omega to be the constant, a constant function being equal to 0. This is exactly the scenario of the Gaussian pulse that we had earlier considered, and we noted that for such a pulse, evidently at t is equal to 0, the maxima, the positive maxima of all the constituent frequencies which we are considering here from omega 1 to omega 6 line up and are perfectly aligned, and as a consequence, if we now sum up these the fields at these 6 frequencies together, okay, the maxima are aligned, and as a consequence we get a pulse out of it, because as we deviate away from the 0 of time on this axis, the pulses start to increasingly destructively interfere, if you wish. That is, the positive amplitude of at one frequency starts to cancel out owing to the fact that at the same value of time other frequencies, a matching frequencies there to have a negative amplitude and interfere destructively, and the further we go away from 0, that is where the thing stands. Okay. So, now if we on the other hand imprint a linear spectral phase, okay, going from omega 1 to omega 6, that is 0 to a pi, and we add successive increments of 0.2 pi over each of the successive frequencies over the preceding one, 0, 0.2, 0.4, 0.6, 0.8 all the way to a pi, then what we have is again do a graphical summing, and we then note that the maxima of these pulses have gotten sort of misaligned, and they have deviated away by a step in the time domain, whereas they are aligned in a sort of perfect synchronicity at a later time other than t is equal to 0, which is this point as it was intentionally shown in the previous view graph. But then what this means is that at this new location where all the maxima are aligned, okay, my pulse has gotten shifted a bit, the pulse essentially has moved forward in time. Okay. So, that is what has happened. Now, we can transform between the frequency and the wavelength domains by using the Jacobian of this transformation, which essentially is minus 1 over lambda squared. So, the change of variables can easily be done, and you can at any point of time recall this by asserting the fact that the energy is the same over when integrated over the spectrum, whether the calculation of this energy, this spectral energy is done in terms of the angular frequency omega, that is the integral of omega from minus infinity to plus infinity, or whether it is or if we do it in the wavelength domain, that is a lambda from negative to positive extreme values, negatives and positives, here again coming owing to the fact that we may have chosen to describe the electric field in such a way that some information, if not extra information, some energy is also distributed on the negative side owing to mathematical processes. So, in which case you integrate these two, I mean you essentially transform the variables on one of the sides and equate the integrands to using the Jacobian, that is d omega by d lambda is minus 2 pi times c over lambda square, which is essentially owing to the fact that c is nu lambda, and you get the transformation between the two domains s lambda and s omega to be mediated by this factor 2 pi c divided by lambda square. Okay. So, as a consequence, if in one domain, the frequency domain, our natural choice always, the pulse is a Gaussian and it has, for example, a simple linear phase variation with frequency, the spectral phase function is linear in omega, then in the wavelength domain the same can appear skewed. Okay. So, what is the purpose of reminding ourselves of all this? That is because very often in the laboratory we tend to measure the spectrum in the wavelength domain rather than the frequency domain, owing to the way in which spectrometers work, and we have spectrometers which can operate over sufficiently long wavelength ranges as shown here, several hundred nanometers, but then they measure intensities as a function of wavelength and not frequency, and these can also be used using techniques we will describe soon in this course, where we can extract the phase information as a function of wavelength. Okay. Now, one should also as a consequence be comfortable to switch between frequency and wavelength domains, or frequency wave number, which are both linearly related, and the wavelength scale, because you measure wavelengths in the laboratory, you may want information in the frequency or wavelength wave number variables. Okay. So, this is a sort of quick recap of what we did in the previous week.